forgetting to record it.
Yeah, I know how that is.
I'm recording now. I can actually set it up so it automatically records, but I always forget to do that too.
Yeah. Yeah, that's what I did last spring when we were Zooming all the time because I would inevitably forget.
All right. I believe we are in the section on motional EMF. It's 23.3. And that means we're only partly way, we're only partway through the chapter. We'll see how far we can get by tomorrow. I doubt we'll finish this chapter this week, but we'll see how far we can get. I suspect we'll probably get about to section 6 or 7 by tomorrow. We'll find out. See what we can do. So let's go ahead and get started here. All right, so we've learned a lot of things about magnetism. We've learned how magnets, magnetic fields affect moving charges. We've learned how they affect magnets. We've learned how magnetic fields can be created by other things, and how you can create an electric current with a magnetic field now. We've learned about how we've learned a lot of things. It turns out that just about everything to do with electricity and magnetism has something to do with movement. And this section is really no different than that. It's just a different situation all over again that results in kind of the same idea. This one is rather interesting, though, this particular situation, because it results in a kind of cascading effect, something that builds on itself quite rapidly. So what we're going to do is we're going to have a magnetic field pointing into the screen here, and we're going to have these two rails that are made of metal and this bar that can slide along the rails and a resistor here between the two rails. And what we're going to do is we're going to slide this bar to the right. Well, as we slide the bar to the right, more and more magnetic field will be inside this loop. And we know that if you change the magnetic field inside of a loop, it will create a current in the loop. Well, the current that is created in this loop will be counterclockwise because it's going to try to counteract the change in magnetic field. The magnetic field is changing into the screen. So the change is this way, change in magnetic flux is into the screen. That means the loop is going to try to create a current that will create magnetic field out of the screen to cancel that change. So that will be the counterclockwise current. And as you pull it more and more and more, you'll get more and more of this counterclockwise current. Incidentally, those two magnetic fields are going to oppose each other, of course. And this is going to result in some kind of force that tries to pull this bar backwards. It's going to resist that in the end. So that's kind of interesting. We call this type of current that's flowing in the voltage that creates that current, we call that voltage across this resistor the motional EMF, which is EMF created by the motion of this bar. So that's they call that a motional EMF. Of course, if you push the bar in, you're going to decrease the amount of magnetic field going into the loop. And so the current will go in the opposite direction and try to counteract that. And so this motion of this changing of the ring, creating this changing of current, creating a changing induced magnetic field, can get quite, it can result in some interesting situations. To calculate that, we're still going to use Faraday's law. It's going to be the number of turns and the flux over time here for that EMF. And of course, the change in flux over time is going to be, in this case, not the change in magnetic field, because the magnetic field isn't changing, but the change in the area of the loop. So as the area of the loop changes in time, now this EMF is created. And the area of this loop is the length of the loop which we're going to call this direction here, this length here, and the width of the loop, which we're going to call this direction here, which we're going to call x. And the change is going to be delta x, this little piece of change here. So the velocity will equal delta x over time. And that's also the change in area is delta x times L. So then we get this delta x over t, which is velocity. And this now gives us an equation for the motional EMF, which is the magnetic field, times the length, or that's kind of the breadth of the magnetic field that you're covering, times the velocity, which is perpendicular to that L. And that will tell you how much voltage you're creating from this movement of the loop, or this expanding or contracting of the loop in a magnetic field. And this actually, well, this is one of the things that gives us a clue to how connected electrical magnetic forces are, and how they are actually the same. They're really the same force in the end. There is no such thing as a static anything. Nothing is sitting still. Everything is moving relative to something else. So if you have a magnetic field out there, it is definitely moving, which means it's definitely creating an electric field, which means there's definitely an induced magnetic field, which means that definitely anytime that you have magnetic fields, you'll have electric fields, and vice versa. It's just the way it is. And so it turns out that these two things combined are a particular force in nature. They're not separate forces. They always exist together. Magnetic force and electric force are different from each other, but they're always present with each other, and they often create one another. So that can be a little bit confusing, I suppose. But let's take a look at an example where we have a satellite connected to a spaceship here, a space shuttle. And in space, when you're near or in near orbit with the Earth, there is a magnetic field from the Earth actually going parallel to the Earth's surface. In this case, it's going into the screen, so the Earth must either be below or above us here, or to the side somewhere. And this is going parallel to it. And they've tethered this satellite with a wire, and the wire has a loop in it. So there's of course going to be some magnetic field passing through this loop. And as this thing is moving, the satellite is moving with the space shuttle. It has a velocity, it has a cross-sectional area in here. And if that is all true, then there's going to be a current running through that because of the motional EMF thing. And so they give us the information: 20 kilo long conductor, moving at an orbital speed of 7.8 kilometers per second perpendicular to the Earth. The Earth's magnetic field, which is this value here, and they want us to calculate this EMF. Turns out we don't actually need to know the cross-sectional area. Remember that the equation only takes into account the velocity when we actually know the length and the velocity. So we just do magnetic field times length times velocity, and we get 7.8 times 10 to the 3 volts of EMF there. And then you could calculate the current if you knew what the resistance was in the wire. But that's, a significant amount of voltage. It's 78,000 or 7,800 volts. So pretty significant. Can actually be kind of dangerous. The thing that they didn't do here, which I wanted to do. Let's see, can I go back? Yes. So if we go back up to the top here and we look at this rail and bar system again, well, I'm going to now replace this resistor with a battery. I'm going to still have the magnetic field here, but I'm going to have a battery here with a switch, and I'm going to turn the switch on. And instead of having a current come through here, and when I move this bar, what I'm going to do is I'm going to drive a current through here, and it's going to make the bar move. And depending on which way I drive it, I can either pull the bar back or I can push the bar forward. And the more it pushes forward, the more magnetic field is inside of it, and the more it will get pushed forward still. It'll actually feel more and more and more force the further the bar goes down the rails. And this constitutes what we call a rail gun in engineering and physics. you can actually create something that can shoot a projectile off of two rails just using some electricity here. And it can, and the further it goes down the rails, the more force it receives. In other words, the more acceleration it receives. And you can give it so much acceleration that you can send things pretty much into space. It can get things going so fast. The problems that we've met with this, and we have built many railguns. There's a great big railgun in my hometown at the laboratory where my brother works. There are railguns in Idaho at the naval testing facility up there, because the Navy is currently testing railguns on many ships to fire projectiles. And why do they do this? Because this is actually very cheap compared to shooting a normal artillery round using chemical propellants. Because chemical propellants, you have to carry them on the ship, you have to replenish them, they have to be taken care of. They're very dangerous because they can explode. They're heavy. I mean, all kinds of things. They're loud. But a railgun is none of those things. I mean, the only thing that you can consider dangerous with a railgun is the flying projectile. Everything else is minimally dangerous. And so, and it also uses very little energy to shoot a projectile. The downside to it is it shoots it so fast that these rails wear down. And so they're trying to figure out a way to make these rails out of materials that don't wear down so much, that won't heat up so much from friction, and make this technology feasible. And when you're going to space, the problem is that it accelerates the space. If you're going to accelerate something to go to space, it accelerates a space ship so quickly that anybody inside of it will die of acceleration. So you can't put people in it. You can put things in it, but even the things that you put in it can be in quite a bit of danger from the acceleration. So they're working on ways to overcome this, or ways to use this in conjunction with other things to go to space. It hasn't really come to fruition yet, but hopefully it will be. When it does, there will be a point in time where space travel becomes much less expensive. Right now, it costs millions of dollars to send somebody into space, and that's down from when NASA was doing it. When NASA was doing it on their own, it was costing billions of dollars to send people into space. But now that SpaceX is doing it, they're doing it for a lot cheaper. When they figure out a way to do this with a railgun and some other propellant technology, it will probably cost thousands to send people to space. And that will very likely be the beginning of the true space age of human beings, where just about anybody can go into space, and we can send all kinds of things and people into space, and we can start settling people onto Mars and to the moon and to other places, maybe even get out as far to Jupiter and go to some of the moons out there on Jupiter, and maybe even someday leave our own solar system. But it's not until we can figure out a cheap and clean and easy way to get to space that's going to happen. Incidentally, they do use this technology in many science fiction books and movies. In Star Trek, they use this. They use a railgun technology to launch things into space, and also in some of Arthur C. Clarke's works. I don't know if any of you are interested in science fiction, but they do use this technology in science fiction to go to space. All right, so let's talk about eddy currents and magnetic damping. So this is related to the experiment that we did not too long ago with this thing, where you turn this thing over and the magnet that's on the plastic just falls super quickly. The magnet that's on the brass falls, but not as quickly. The magnet on the aluminum falls, but very slowly, and the one on the copper falls the slowest. And the reason for that is because it's a changing magnetic field near an electrical conductor. And the plastic's not an electrical conductor, but these three are. And depending on the amount of electrical conductance, you can actually create more current. So in the copper, it's creating a ton of current in it. And the current is what we call eddy currents, which means they're kind of just making their own loops of current. So here you can see this is a swinging piece of aluminum, swinging between a magnet. When you swing a piece of aluminum like this, a solid piece, you can create big loops of current, and that big loop of current will be created in such a way to counteract the magnetic field change that it feels as it goes in between these magnets, which means it'll be in the opposite direction, which means it will actually slow this thing down. It'll actually try to stop this thing, and it will actually stop it pretty quickly. However, if you cut a bunch of slits in the aluminum, it won't work out so well because there's not enough room for these eddy currents to get going. You can make tiny little eddy currents in here, but you can't make lots of big ones. And so these tiny little eddy currents will not slow this down nearly as much, and you won't get this magnetic damping, we call it. Damping is a slowing down of the movement. And so this is kind of like the opposite of the previous section where we created movement with current. Here we're damping movement with current. And it can work either way, depending on the direction of the current and the purpose for it. So here they show kind of those tiny little currents compared to the big currents that can be created as you swing it through a magnetic field. And we actually use this all over the place. This is used in many things in the world in general. If you've ever used a scale in like a chemistry class, one of these old-fashioned scales, they actually use magnetic dampers. They put magnets in a big disc of metal, usually aluminum. And the reason for that is to keep the scale from kind of wobbling back and forth, which it would normally do if you didn't have that. So it slows those things down quite a bit. This is used to separate metal from paper and plastic and other junk at a garbage disposal area, right? And your local, maybe not in our local junkyards, it's maybe not used, but it is used definitely in big cities where it really matters that they separate this stuff because they have so much garbage. But the magnet will actually stop anything made of steel pretty much in its tracks, but it will slow down things made of any kind of metal. And so you can actually get things to slide down more quickly and other things to slide down more slowly. And then it can be easier to separate these things out, even if they're made of aluminum or something that's not magnetic, not ferromagnetic anyway. It's also used in metal detectors. Here they're using a metal detector to look for explosives, weapons, and other things. But you might see people on the beach or in a park somewhere using a metal detector to find coins or jewelry or something like this. And you actually have to move this. This thing, you can't just sit it and detect metal. It actually has to be moving back and forth to detect it because the movement matters. It's essentially what this is it's a loop of coil. It's a coil of wire down here, and the coil of wire is connected to some electronics up here which detect the change in current going through those coils as you go over something metal. It's also how the metal detectors in the airport work and anywhere else, library. As you walk through the metal detector, it creates a current in any metal that's on your body. Those currents create a magnetic field that oppose the magnetic field in the coils that are in the metal detector, and that the coils in the metal detector then experience a change in current. And then you can go ahead and detect that change in current and know if somebody has something metal on them. And they can adjust it so that it detects big metal things or small metal things or whatever. They can adjust it so that it's designed specific ways. So you have the same thing on roller coasters. So this is a roller coaster track, and right in here are just a bunch of permanent magnets. These are just a bunch of really strong permanent magnets. And on the side of the car in the roller coaster, there are big plates of metal. And as the big plates of metal come through here, the magnets induce a current, an eddy current in the metal. The eddy current creates a magnetic field that opposes the magnetic field here, and those magnetic fields repel each other and slow down the car of the roller coaster. Now, why are these great? Why is this used on roller coasters? Well, on roller coasters, it's really important that you have brakes that will always work no matter what. These brakes will always work. There's no mechanical parts that can break. There's nothing that can go wrong because they won't turn on or something. They're always on. As long as the car goes through here, it's gonna slow down the car. The only way these won't work is if the car doesn't go through, and then you don't need it to stop, I guess, at that point. It's already stopped somewhere else, or it's going somewhere else where it should. So So you have all kinds of situations with it. Those are just a very few of them, where eddy currents are used in the world. All right, so now we're going to move on to electric generators, and we've actually talked about these a little bit before when we talked about motors, which was, I believe, the last chapter. Yep. So we talked about motors in the last chapter, and this is the exact opposite of a motor, where instead of having a battery up here connected to commutators and brushes that drive a current through here and cause this thing to flip around and around and around in the magnetic field, now we're going to actually connect those commutators to some circuit, in this case, just some kind of current meter, and we're going to turn the handle and make this thing create a current because it's moving. So now that it's turning, the magnetic field going through the loop is changing. So a motional EMF is created in the loop. That motional EMF creates a current and drives a current through the circuit. This particular generator is set up so that it creates an AC current, one that goes one way and then another way and back and forth, depending on which way the coil is pointing in the magnetic field. And that will create a current like we use in our house. Our house is an alternating current or an AC current that goes from a positive 120 volts to a negative 120 volts, or you could think of it more as a current going one direction, then a current going another direction, then a current going one direction, then the other direction, back and forth and back and forth and back and forth. And that just pushes the electrons around in our toaster and heats up the toaster elements, or it pushes the electrons around in the motors of the motor of our dishwasher and causes the dishwasher heads to turn and to spin, and whatever it does, it drives current back and forth and causes the electrical devices in our house to function like they should. In this particular case, they actually want us to calculate the EMF. They want to know the average EMF induced if we're turning this thing through here, and we're going through 1/4 of a revolution. So we're going from theta equals 0, theta equals 90. We're going to do this in 15 milliseconds, and it's going to be a 200 turn circular coil. So N, that's big N, equals 200, and it's going to be a 5 centimeter radius. So that's going to give us some idea of it says it's circular, but it shows that it's square or rectangular, but it is circular. This will give us some idea of our area. And they also tell us the magnetic field. So if we use Faraday's law, we should be able to figure this out. Remember that Faraday's law says that the EMF is equal to negative the number of turns in the coil times the change in flux over time. We know the time, we know N, we need to figure out the flux. Well, the flux is equal to the magnetic field times the change in the area that it's going through. And the change in the area that it's going through is going to be dependent on the angle that the loop has with the magnetic field. When the loop is at 90 degrees to the magnetic field, it's like this. So that the magnetic field is going parallel to loop, that means there's 0 magnetic field going through it. When the loop is at 0 degrees, it's this one here where it's facing it's facing both magnets, and all of the magnetic field is going through. So our delta flux, or the change in our magnetic field, is going to be the maximum minus the minimum, or vice versa. And we'll take minimum minus maximum because we're actually going from the minimum to we're going from the minimum to the maximum. So it'll be maximum minus no, we're going from maximum to minimum, sorry. So it'll be 0 minus 1.25. So, and 0 minus 1.25 is minus 1.25. Since there's a minus out here, those two minus signs cancel to give us positive 1.25. So our total change in magnetic field is 1.25 Tesla. Then we calculate our area. They do that somewhere up here. I don't know where they do it, but oh, here it is right here. A equals pi r squared. So they calculate that right there, and there's our area. It's a very small area in meters squared. Remember that you have to convert your 5 centimeters to meters, to 0.05 meters. And then we divide by the 15 milliseconds, which is 15 times 10 to the minus 3 seconds. Now we've got everything in there, and we calculate and we get 131 volts. So you could actually, with a generator of 200 turns, turning at 1/4 turn every 15 milliseconds. So you're doing, that would be 4 turns every 60 milliseconds. That would give you about 40 every 600 milliseconds. So you'd have to turn it about 50 or 60 times per second, which is what we call 60 hertz. So this actually is how energy in our houses could be created. You'd have to turn the handle 60 times every second, which is really fast. You'd have to have 200 turns of wire on there. And you'd have to have a magnetic field of 1.25 Tesla, which is a pretty powerful magnetic field, actually. So it takes a lot of oomph to create this power using this size of coil. Now, if we used a much larger size coil, because 5 centimeters isn't very big, that's a coil like this big. If we used a coil much bigger, then maybe we could do better, right? Because the size of that coil is up here in the numerator. So the bigger that gets, the more voltage we can get. The same goes with the number of turns. The other way that you can get bigger voltage is to have a much bigger magnet, but that's a very big magnet already. Also, you can just go much faster, which is already difficult because 60 times per second is much faster than a human can turn it with their hands anyway. You could do it on a bicycle maybe. You could hook this up to a bicycle and then turn it with your bicycle and maybe get close to 60 times per second, but it would be difficult even then.
I have a question.
Yes.
Is this the same type of thing? You see those radios that are you crank them to,
yes, exactly. Yeah, that's exactly what they do with those crank radios. They connect it to a generator like this, and they create an AC current, and the AC current runs the radio. They actually may do it with a DC current, but all they do to do that is they put a commutator and they have one commutator and 2 halves of a loop, and then they get a DC current. So they may deal with a DC current, but it's still the same concept in its basic form. Yes. And they even do the same thing. You may have seen, have you ever seen one of these flashlights that you just shake? And then you can use it as a flashlight for a while, and then you can shake it, or you can just walk with it or whatever. That's a very similar concept. But instead of rotating a coil through a magnetic field like this, what they do for one that is a shaking one, let me see if I can find my drawing tools. Where are my drawing tools? There they go.
Yes, my husband has to have all these things, so.
Yeah, for the shaking one, what they do is they have a capacitor inside the flashlight that can hold charge, and usually some resistor connected to it. And then they have these coils of wire that are in the handle of the flashlight, many coils of wire. And these coils go up and then back down again here to the capacitor, right? And there's a resistor in there too somewhere. But anyway, as you're shaking this thing, there's a magnet that goes back and forth down through the coils. And that changes the magnetic field through the coils, and it drives a current through here, and it charges up this capacitor. And then when you switch on the flashlight, it connects the capacitor to the bulb. Then you can use it for a little while. I mean, the downside of this is that the capacitor only has a certain amount of capacity, so you can only charge it up so much. And usually that will give you for a really big size capacitor, and if you put a lot of loops on here, you can get the flashlight to go for a few minutes maybe at the most, and then you have to charge it up again. But if you're walking with the flashlight, then this thing is kind of rocking back and forth, it will still charge it up. And they've actually even made this, so this is a different kind of generator. It's a linear generator instead of a rotational generator. They've actually made linear generators that are connected to muscles in the body. So your muscle is connected right here. And there are muscles in the body that are just twitching all the time, that just that expand, contract all the time. And really their only purpose is to kind of keep our bodies warm. And so what they've done is they make these tiny little generators and connect them to the muscles so that it's driving this magnet through these coils and charging up, instead of a capacitor, it charges up batteries. And the batteries can be used to run medical devices like pacemakers. And that's something that has been done. And there are many other ways that you can create electricity by changing magnetic field through coils like this. In fact, one of the things that can be done that was just demonstrated in MIT, I think is where they demonstrated it. You can actually have something like this. It's not exactly like this because it's instead of just having a coil of wire here, it actually has a special kind of antenna. Have you ever seen these card keys at hotels that you can just put up against the door and it opens the door? You ever seen those? So they call that an RFID scanner, which stands for radio frequency induction device, I think, or something like this. And what that is it's a particular type of antenna made in a particular shape called my brain just stopped. What happens when you graph a function that is dependent on itself? You get a fractal. There we go. So it's called a fractal antenna, which is kind of a geometric shape that repeats itself. You've probably seen fractals before. We can actually look at it here, maybe. So fractals, these are fractal pictures. For example, this right here is the Mandelbrot fractal. And this one, I can't remember what that one is, but many things in nature actually imitate fractals, like crystals of different kinds. This is like an ice crystal, it imitates fractals. But there are many, many fractals that you can create using mathematical functions that are essentially dependent on themselves. They call themselves. They're called a I can't remember any of my math terms these days. But anyway, these functions, you can also make antennas out of these shapes, of geometric antennas with fractals. And they look kind of like this. They have these repeating shapes to them. And you can make an infinite number of these that are all completely different from each other. And each one of these antennas interacts with radio frequencies or with electromagnetic waves in different ways. So if you build one of these fractals into a card, like a little credit card, and then you bring it near a doorknob that has electronics in it that are designed to interact with these fractal antennas, then that your particular fractal antenna in that card will give a particular signal, a particular type of current inside the electronics in the door. And so every one of these cards has a different fractal antenna. And if you bring it near the door and that door is coded to accept your code, your particular signal, then it opens the door. And if it doesn't open the door. And that's the beauty of those cards, is that they are one-time use. You can make as many as you want of any different kind. I mean, there's no end to the types of fractals you can make, infinite number. Well, you can also build these fractal antennas and connect them to this kind of thing, where they can absorb many different kinds of frequencies. Instead of interacting with an electronics to give a particular frequency, they can absorb many, many kinds of frequencies. And the air outside is full of radio frequencies. There's radio frequencies from artificial sources, or man-made sources, and also just from naturally occurring sources all the time, all around us all the time, including the light from the sun is essentially a electromagnetic signal. And if you can create an antenna that will essentially capture that energy, capture those waves and interact with those waves, it can actually transmit that into a coil and create a magnetic field, which can then create electricity and charge up a battery. Well, how nice would it be to have a cell phone that you can charge just by walking around or standing around in the park or whatever? And that's exactly what is coming up next. The next real big change in cell phones, I think, will probably be a cell phone that will just charge itself just by being in the presence of electromagnetic radiation, which it is always in the presence of. You even have electromagnetic radiation coming out of your brain. So every time you put your phone up to your head would charge your phone, you know? So, so this is actually kind of exciting, kind of exciting stuff to be free from needing batteries for small devices like that. Probably wouldn't work for quite a while to charge things like car batteries, but eventually it would probably work. And eventually there will be a point where you can charge something specifically from a distance by shining a laser on it or something. So all you need to do is be able to see something, you can charge it up. And that's something that's been thought about for years, but is finally coming to fruition, and will probably be developed in the next 5 or 10 years, I would guess. Where were we? Yeah. Okay. So let's see. Here they actually show a generator that's powering a light bulb. This is a DC generator where they split the commutators so that the brushes switch sides every time this thing rotates around. And it's going to send only a positive EMF to this light bulb, or if you switch it around, a negative EMF, but it will never go underneath and be positive, then negative, positive, then negative. Whereas this one, where it has the two commutators separately connected to either side of the loop, will give an AC current that goes positive and then negative, then positive and then negative. And of course, and this is a voltage, but the current will follow this. The current will also go one way, then the other way, one way, then the other way. And so right in the middle here, it's going to go to 0 at some point. But light bulbs don't care which direction the current is going, as long as it's an incandescent light bulb. If this is a light bulb that is made of an LED, just a regular old LED, some LEDs do not like the current to go both ways through them. So it would only light up maybe when it was up here, or maybe when it was down here. In this case, it's going to just blink on and off, kind of, it'll wobble a little bit in its brightness. If it's wobbling 60 times a second, you won't be able to see it because your eyes can't see something that fast. And also it doesn't cool down fast enough for it to really change its brightness. So anyway, here we can actually, we can use this. So they go through this calculation up here that I didn't go through, but they go through this calculation to show when this is at its maximum EMF. Well, it's at its maximum EMF, of course, when the sine is at its maximum, because the sine is the only thing changing in this equation. So the maximum EMF is just the number of turns times the area of the loop times the magnetic field times omega, where omega is the angular frequency of the turning of this thing. Angular frequency equaling 2 pi times the regular frequency. So if it has a frequency of 60 hertz, then you multiply that by 2 pi and you get the angular frequency. And so here we use that equation to calculate the maximum EMF of this particular generator in the previous generator, actually, that has EMF of 60, or I'm sorry, an omega of 60. Well, not quite 60, whatever it was. I can't remember what it was. But they have all the information and you plug it in. It's got the 200 turns. So here they actually calculate the period of, they calculate omega by taking the period and dividing it by, multiplying it by pi over 2 and dividing by the period. There we go. And they get 104 radians per second for omega. Then they knew the number was 200. We knew that. We also calculated the area in the previous problem. There's the magnetic field. And then there's our omega. 206 volts is the maximum voltage. Whereas the average we found was like 130 or something like that. So the average is somewhere in here. The maximum is up here. And here we see a turbine generator. In this case, you have steam coming in through these pipes, and the steam pushes on these vanes, and they've opened it up here so you can see all the vanes. But the steam goes through the vanes. There's gaps here, and it goes through them. And every time it goes through them, it pushes them in this direction here and causes the thing to spin. And this thing is connected to a huge generator with a bunch of turns of coils. Now, they don't have just one single coil like this. they have one coil this way and then another coil turned at a slightly different angle and another one at a different angle. So no matter which direction it's pointing, it's making some current. It's a hugely complex looking coil. In fact, we should take a look at it because it is quite interesting. So let's do that really quick. Where did it go? I don't see it. Let's do it right here. So generator coil. So here these are more complicated. So here's an idea, this idea where you have multiple coils at multiple angles turned, and then they have these coils that create the magnetic field on the outside for that. Here you can see this is a big one at a power plant. So that's what it looks like when you go to a power plant and you see the generator. It's this huge thing and multiple coils in there. That's actually a different generator than I was wanting to show you, but let's try to find let's say let's see if they're actually showing. I mean, that is the one that's part of it. It's not the part I want to show you. That's all right. They're not going to show us the inside of one of these things, I guess. That's all right. But anyway, it looks like that one that we saw the drawing of anyway, where you have multiple coils at multiple angles, and they're packed much more tightly together when you're actually creating energy at a power plant. All right, so that takes us to the end of section 5, and we will pick up again on section 6 tomorrow. We will see you then.
Thanks.
Thank you.